Okay, so we are starting section 2, specifically 2.1, day 1. There's actually 2 days in this specific unit. So we're going to start talking about derivatives and rates of change, and the fact that they're pretty much the same type of idea. They're just one derivative is a special type of rate of change, and we'll talk about that. So we're going to compare instantaneous and average rates of change. We've actually talked about this before. We've actually seen this. So the idea is, if we have a curve, whoops, let's actually try to draw something here. We have a curve, and I've got a point on that curve, and we'll call it P. Okay, that point is associated with an endpoint or some kind of a point here. We'll call that A. So my point P is going to be the point A, f of A, which is just its y value. If I want to find the slope at that specific point, well, we know that to find the slope of something, you really need 2 points. The problem is, I can't take 2 points on the line, on the curve, without that creating a secant slope. So we were to take a second point anywhere, we'll just put it up here for right now, and we'll call it Q. And we'll call the related x value for Q, we'll call that x, just because we need a different name other than A. So that makes our point the point x, f of x. Well, we know we can find the slope between those 2 points. Yeah, I can take a slope. See how well I can draw this. Okay, so there is a line that goes in between those 2 points, between P and Q, and we can find the slope there. That's just a slope formula. So the slope between the line segment of P and Q is going to be a y2 minus y1 over x2 minus x1. So y2, f of x, minus y1, f of a, over x2, which is x, minus x1, which is a. That's the slope between the 2 points P and Q. All right, so now what we want to do is we want to take that Q point and we want to move Q closer and closer and closer to P. So if I move Q to here, then my slope starts to look like this. Okay, that's the average slope between those 2 points. Then if I move Q to here, now the slope is going to look, let's go with purple, going to look something like this. Ultimately, what I am trying to find is I'm trying to find the slope of this specific piece right at P. We want it to be a tangent slope. Well, the problem is, again, you cannot take another point on the curve and let that be a second point that's going to be another point which is going to be the exact same point as P. You can't do that. You can't take the same point twice. But what we can do is we can say, okay, I know that whatever the slope of the curve is going to be exactly the same thing as the slope of the tangent line. Well, if I can figure out what the slope of that tangent line is, then we're going to be able to figure out the actual slope at P. So as I take Q and I move it closer and closer to P, what I am doing is letting the x value here, letting this x value, whoops, didn't want to use green there, letting this x value get closer and closer and closer to A. So as x approaches A, the secant line is going to become a tangent line. So what that's really saying, kind of wrapping this all up, is that what we have up here is the slope of a secant line. What we have down here is the slope of the tangent line because I am taking the limit of those secant slopes as x gets closer and closer to a. So as I let that distance between x and a become so small that we can't even tell the difference, we are taking the limit as x approaches a, not x equaling a, but as x approaches a of the secant slopes. That's going to become the slope of the tangent. All right, so let's go ahead and take a look at how all this works. So we want to find the equation of a tangent line to the parabola x squared plus 2x at the point 2, 8. So again, we know the parabola is it's not linear. You know, a parabola is going to look something like that or whatever. I'm not going to draw this one specifically, but it's definitely not linear. So at the point 2, 8, we want to find out what the equation of that tangent line is. Well, you're going to hear me say this a lot of times. To write the equation of a line, you need 3 things. The most important of those is the slope. You need the slope of the line. The other ones is you need an x and a y value so you can go ahead and finish off the equation of your line. We are going to use the point slope form of a line. And the point slope form of a line, in case you don't remember, is y minus y1 equals m times x minus x1. And the reason we're going to use that is because literally it requires you to know the slope and a point. The slope, which is m, and your point, which is your x1 and y1. That's what you're going to plug in. You'll have the equation of a line. It's also very easy to manipulate from that form to get it into y-intercept form, which is our more common y equals mx plus b. So let's go ahead and work through this problem. So we're going to find the equation of the tangent line to that parabola. In order to do that, we're going to have to find the secant slope and then take the limit as x approaches a. Okay, what is a? Well, a is your x value. That's all it is. It's the x value of the point that we're interested in. This is a. So we're going to write that down. A is 2. F of x, well, that's easy. That's the given function. So that's just x squared plus 2x. Probably should have put a third thing on here, f of a. So we'll add that in there. F of a is going to be the function evaluated at our x value. So the function evaluated at our x value, well, you could certainly plug 2 back into here and get a value, but they gave that to us because that's what this is. That's f of a, so that's 8. And if you plug 2 back in, you would certainly see that. Now, if they don't give you the 8, if they just tell you that x is 2, then you'll have to find the 8 yourself. All right, we have everything we need. Let's plug all this information into our limit. Figure this out. So we're going to take the limit as x approaches a, but a is 2, of f of x, that's x squared plus 2x, minus f of a, that's 8, over x minus a, but that's 2. Okay, we know that if we plug 2 in, specifically in the denominator, it's going to give us 0. It's also going to give us 0 in the numerator. So this is going to be an issue that we're going to need to go ahead and factor. So we're going to factor that numerator, hoping to get an x minus 2 out of this thing. That's going to cancel out the denominator for us. So we should get x minus 2, and then it should be x plus 4 on top. Okay, you should be able to see the x minus 2s are now going to simplify to 1. So we're going to get the limit as x approaches 2 of x plus 4. We can now use direct substitution, and we get 6. What is that? Well, we just found the limit of our secant slopes as x approaches a. So what we found was the slope of the tangent line. So 6 is the slope of the tangent line. The slope of our tangent line is 6. We have our x, we have our y. We can plug them into the point slope form. So y minus the y value, which is 8, equals the slope we just found is 6 times x minus the x value, which is 2. That's it. That is the equation of the tangent line to the parabola y equals x squared plus 2x. Now here's something you can try just to make sure. In your calculator, you can go ahead and plug in y equals x squared plus 2x so that you can actually see that graph on your calculator. Then you can actually manipulate what we just found to solve it for y. All I'm going to do is add the 8 to the right side, so you're going to get 6 times x minus 2 plus 8. You can obviously go ahead and simplify that, distribute the 6, and you'll get 6x minus 12 plus 8, so 6x minus 4. But you can also just type it in like I have here, and you will see that that equation, that linear equation, is tangent to the parabola at one point, and that point is at the point 2, 8. So you can try that. That's not something I'm going to show here. All right, so there's technically another definition for the slope of a tangent line, but it's really not any different. It looks different a little bit, but it's not really any different. So we're going to start off with the one that we just had. Limit as x approaches a of f of x minus f of a over x minus a. Well, let's just say that the denominator here, we're going to call x minus a h. That's what we've got here. We're just going to call it a different letter. So we're calling that x minus a different variable h. Well, if that's the case, we can take this formula right here and solve it for x simply by adding a to both sides. If I add a to both sides, I'm going to get that x equals a plus h. And h literally is the distance between x and a. So if I am taking x minus a, or like we talked about on the previous page, I am letting the x value get closer and closer and closer to a. If that's the case, I am letting the distance between x and a get really, 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 really small. And since h is that distance, we are going to let h become, or approach, actually that should not be equals, it should be approach 0. So as x approaches a, h is approaching 0. As x approaches a, x and a are getting very close together, so the distance between them, which is h, is getting closer and closer to 0. So now all I'm doing with this second equation down here is I am substituting. Okay, so right here, a plus h. Well, that took the place right here of x, because x is a plus h. So I just replaced the x with a plus h. Still got minus f of a. That hasn't changed. And then the only other difference down on the bottom is that this h now took the place of the x minus a. And notice that this h is approaching 0, as opposed to x approaching a, but they mean the same thing. I am going to tell you that this is probably the equation that you will use most often. It's usually the easier one. Both of them work. One of them is going to be in place for people who feel more comfortable with expanding functions. The other one is going to be in place for people who are better with factoring or manipulating algebraically. Everything's going to be algebraically manipulated. But okay, so let's go ahead and see how this works. So this time, we're going to use the second definition. So we're going to do it with the limit as h approaches 0 of f of a plus h minus f of a over h. So the first thing is we're going to write down f of x. Well, that's just the original function, 1 over x minus 1. The a value here, that doesn't change. That's still the x value that we're approaching, so that's 2. But we do need a couple of other pieces. We need f of a plus h. So we need f of a plus h. Well, in this case, our a value is 2, so that's f of 2 plus h. And now to find that, we're actually just going to take 2 plus h and plug it in for all of our x's in the original equation, because that's what f of something means. It means take what's inside the parentheses, plug it in for your variables. So what we're going to get is 1 over 2 plus h minus 1. We'll simplify that. because I've got a 2 and a minus 1 in the denominator, so I've got 1 over 1 plus h. Okay, and the other thing I need is f of a. Well, they gave that to us. That's our y value. That's 1. So we'll just write that down. So f of 2, in this case, is 1. Again, that was given to us. If we didn't know it, you plug 2 into the original function, you still get 1. All right, now we have everything we need. So let's go ahead and find our limit. The limit as h approaches 0, the nice thing about using this form is h will always approach 0 because we want that distance to become nothing. So the limit is going to be f of a plus h, which we found to be 1 over 1 plus h, minus f of a, which is 1, all over h. And the general idea here in all these types of problems is we want to get rid of the part in the denominator that is giving us an issue. That is that h. Because if I plug 0 in there, I am dividing by 0. We cannot do that. So what we need to do is we need to manipulate this equation. To manipulate the equation, I could either combine the numerators and then do a fractional divide, or I can just get rid of the complex fractions all at once, which is my specific choice. So I'm going to multiply everything on the top and the bottom. Whoops, didn't mean to put a t in there. By 1 plus h. That way I'm maintaining the dynamic of the fraction. It's not changing it. So I'm going to multiply 1 plus h times this one, and times this one. So I'm not changing anything. I'm just going to change the way it looks. So I'm still taking the limit. If I multiply the 1 plus h times the first fraction on top, I get 1 plus h over 1 plus h, which is 1. Minus, multiply 1 times 1 plus h. This is why I put it in parentheses. Keep it in parentheses, or you might forget to distribute the negative 1. And then on the bottom, good rule of thumb here, do not distribute. The reason we don't want to distribute is we're trying to get rid of that first h. If you distribute, you're just going to have to factor it back out later. All right, let's simplify. This is something you must do in multiple steps. In the numerator, you can simplify by distributing the negative sign. So you're going to get a 1 minus 1, which is 0. Don't forget to distribute the minus sign to the h, which gives you minus h, over h times 1 plus h. Some of you may have already seen that those h's are going to end up dividing out. You cannot do that all in one step. You can't do that in the previous step and do it all at one time. It must be shown that you understand order of operations. Now we can get rid of those. And that is going to leave me with the limit as h approaches 0 of negative 1 over 1 plus h. Now that I have gotten rid of the undefined value in the denominator, I can directly substitute h0 in, and when I do, we get negative 1. That is the slope of our tangent line. A lot of work to get to that point, but that's the slope of the tangent line. So now I've got everything I need. I've got my slope, I've got my x, I've got my y. Let's write the equation of the line. The equation of the line is going to be y minus y1, which is 1, equals slope, negative 1, x minus x1, so x minus 2. And once again, you can go ahead and distribute the negative 1 and add the 1 from the left-hand side over to put it in slope-intercept form, but this is a perfectly acceptable equation of the line. Okay, we are going to stop the video there. We're going to come back with a second video and hopefully finish this section off. If not, we'll do a short third video.